So in this example, we would like to discuss how to do superposition when there is dependent sources inside the circuit. Let's first look at a circuit diagram. So in this circuit, we have two independent sources, V1 and V2. And we have one dependent current source, whose value is controlled by this voltage V as defined between the voltage between this pair of terminals. And we also have the output voltage, which is chosen as voltage across this resistor, R1. Now the question is, how do we calculate VO? So in order to calculate this circuit, we notice that there are two independent sources, so we can do superposition. So we can first turn off V2 and only keep V1 inside the circuit and see what is the contribution from V1 onto this output voltage. Let's draw the equivalent circuit. Remember, removing a voltage source is equivalent to put a short there. So this is V1, this is R, this is R, and let's call this voltage as VA. And then the dependent source should depend on GVA, and this is R1. Now let's call the output voltage is VOA. So now the question is, how do we calculate VOA? First of all, we notice that this circuit can be calculated using node analysis. Let's choose the ground node, which is the bottom line. And then we can easily see that the voltage VA is 1/2 of V1. This is because this resistor R and this resistor R form a voltage divider. After we decide on VA, we can get the dependent current source value, that is GVA. Now let's look at output voltage. We notice that the output voltage is the same as the node voltage E. Again, for node E, we can utilize KCL. You'll notice that there are only two currents that go inside this node, which is GVA plus 0 minus E divided by R1. That should be equal to 0. So you can utilize this relationship to calculate E, which is equal to GVA times R1. This makes good sense because R1 is the only path that this current can flow through. So actually the dependent current source, GVA, will flow in this path. So the voltage across R1 is E is equal to GVA times R1 using Ohm's law. The output voltage, VOA, is also immediately equal to E, which is equal to GR1 times VA, which is further equal to 1/2 GR1 times V1. So now we consider the contribution from the voltage source V1. Next, let's consider the case when we turn off V1 and only keep V2. Now let's draw the equivalent circuit when V1 is turned off. So the equivalent circuit is like this. Now let's call the voltage contribution from this V2 as VOB. Still have R. And now this voltage, let's call it VB. So this is G, VB. Again, we can utilize similar techniques to calculate this VOB. First of all, we notice that those two resistors again form a voltage divider. So VB should be equal to 1/2 of V2. And then we notice that the current through the current source only flows through R1. So that means voltage across R1, which is VOB, should be equal to GVB times R1. Replace expression of VB, we get 1/2 GR1 V2. So far we have calculated the contribution from V1 and V2 onto the output voltage separately. For superposition, we need to combine them together in the end. So in the end, the total output voltage, VO, should be equal to VOA plus VOB. So we can rearrange it. It can be expressed as 1/2 GR1 times V1 plus V2. So this is output voltage when there are two independent voltage sources inside the circuit, as well as one dependent source. Let's look at this final output. You see it's equal to V1 plus V2, of course, multiply some coefficient. You can imagine you can utilize this circuit as an analog adder. Basically, you add voltage V1 with V2. Previously in the lab, you also learned you can directly utilize resistance network to make an adder, where you add the signals from different channels. The advantage of the circuit that we discussed today is that it can optimize the output performance. So that means this circuit will be less sensitive to your load resistance. For the circuit with purely resistance network, depending on the load resistance, the output signal will be high or low, depending on the voltage distribution between the resistance you use as well as the load resistance. However, for this one, you can design it much better to make sure that the output voltage is less sensitive to the load resistance. Of course, because here you have this dependent source, you can also make sure that this coefficient is large, so you get some gain after you add those two signals. So again, those are the two advantages associated with dependent source. One is you can get gain, and secondly, you can optimize input-output performance.